Okay, so let's talk about standard PTG. It's that fantastic all-arounder, right? The workhorse filament most of us reach for.
Absolutely. It has great chemical resistance, pretty good temperature stability, and it's, relatively easy to print with.
But here's the reality check for you, our advanced listener. Standard PTG is, well, it's rarely the best material for anything truly demanding.
Right, it's a jack of all trades.
Exactly. So what happens when your project suddenly needs something extreme, something non-negotiable, like maximum stiffness for a high-precision sensor mount?
Or even guaranteed fire safety in an electronics box.
Right.
And that's the moment you have to stop thinking about just printing anything and
Mhm.
start thinking about material specialization. Standard PTG is just the foundation. The real deep dive is into these highly engineered variants.
So our mission today is to cut through some of that marketing noise and really understand which specific material is for which specific high-demand job.
That's the plan.
We're going to unpack the structural composites, carbon fiber, glass fiber, and see how they just fundamentally change the polymer. Then we'll pivot to, well, to two major industrial trends: sustainability with RPG and the need for incredible speed with hyper PTG.
And we have to cover the non-negotiables, like the flame-retardant V0 variants for safety.
We've got a comprehensive stack of sources here. Okay, let's unpack this, and let's start with the one that's all about maximum rigidity.
That would have to be PETG-CF.
Carbon fiber.
Yep. This is a composite where the standard PETG polymer is reinforced with short, chopped carbon fibers. And they're loaded in pretty high, usually between, say, 10 to 20% by weight.
And these fibers aren't just for looks, right? They're not just decoration.
Oh, not at all. They radically transform the plastic's DNA.
And when you look at the numbers, that transformation it's stunning. The carbon fibers, they act like a microscopic rebar.
That's a great analogy.
The stiffness, which I guess engineers measure as the tensile modulus, that can be up to 3 times higher than pure PTG. And tensile strength, the force it can take before it breaks, can easily double.
Let's pause on that jargon for a second. Tensile modulus.
Yeah, good idea.
When we talk about stiffness, think of holding, I don't know, a plastic ruler on its end and trying to push down on the middle. Pure PTG might bend quite a bit.
Sure.
The carbon fiber variant resists that bend 3 times more effectively. It just holds its shape under pressure.
Yeah.
And that matters enormously for things like precision jigs, drone frames.
Or mounting brackets where any little bit of flex could cause a failure or throw off a measurement.
Exactly. You're talking about parts that have to maintain their shape, their dimensional stability under a constant load.
The sources also point out it gets you better thermal resistance and that really nice matte finish. It does a great job hiding layer lines.
It does. Well, what's so fascinating here is the trade-off. There's always a trade-off. This massive increase in stiffness and strength, it comes at a cost to its flexibility, its resilience.
Yeah.
By tying those polymer chains together with these rigid fibers, PETG-CF becomes significantly more brittle.
So it can withstand a huge amount of force, but once it hits that breaking point,
It snaps. Clean break.
So if I'm printing, say, a protective case for a tool that I know is going to get dropped and I need it to absorb that impact, maybe bend a little.
Standard PETG is actually better for that job.
Because it's tougher. It yields.
Precisely. But if you need that exact shape under a constant load, like a manufacturing jig or a robotic arm part, the stiffness of CF is invaluable. You're specializing the material for zero deflection, and you're accepting that you lose some impact toughness.
Okay, so if you do choose this material, you have to deal with what seems like the #1 hurdle, the thing that catches everyone out.
I know where you're going with this.
The nozzle. You have to use a hardened nozzle. Is this really a non-negotiable step?
It is absolutely 100% non-negotiable. Carbon fibers are extremely abrasive. They're basically microscopic ceramic shards that you are dragging through your nozzle at high speed.
So a standard brass nozzle.
It would be ruined. The bore gets widened, the shape gets distorted in just a few tens of grams of filament. Your extrusion immediately becomes inconsistent. You need tool steel, hardened steel, or a specialty nozzle with a ruby tip.
And our sources consistently recommend going with a slightly larger nozzle, like a 0.6 millimeter or bigger. Why is that?
That's all about reducing the risk of clogging. Those little chopped fibers don't like making tight turns. A larger diameter just allows for better flow and the better distribution of the fibers in the polymer.
And you also have to print hotter.
Yeah, but you need to bump that temperature up maybe 10 to 20 degrees Celsius higher than standard PETG. That just ensures the polymer fully melts and coats the fibers properly, which is critical for strong layer adhesion.
It really brings into focus how specialized this is. If you want that incredible stiffness, you're dealing with more cost, more hassle, and that brittleness.
Mm.
But what if an application needs that high strength, needs the temperature resistance, but also has to handle some rough treatment, some impacts?
How do you minimize that brittleness?
Yeah.
Well, that leads us directly to the glass fiber alternative, PETG-CF. This gives you a fundamentally different balance of properties. You're deliberately pulling back from that maximum rigidity of carbon fiber to get back some of that impact performance.
So give us the breakdown. What's the exchange rate there?
Well, glass fibers give you a smaller increase in stiffness compared to CF. Maybe a 50% increase over pure PETG instead of 300%.
Okay.
But, and this is critical, they retain or even slightly improve the impact resistance.
Yeah.
The toughness. The material is just much less prone to that brittle failure. Think of it this way. CF gives you a diamond. GF gives you a really, really strong plastic mallet.
I like that. So it's the ideal choice for, say, robust mechanical parts, things that need to withstand stress and heat, but where impact is a real possibility.
Exactly. Heavy-duty fixtures, maybe parts on a production line that might get knocked around. You're trading that absolute stiffness for reliable impact performance.
And there are other benefits too, right?
There are. Glass fibers are cheaper, and they're significantly less abrasive than carbon fibers. I mean, you still want a hardened nozzle as a best practice, but the wear is far, far slower.
And you can get it in colors.
And you can get it in colors. Carbon fiber composites are almost always black.
That's a great synthesis of the mechanical extremes. So let's leave the world of fiber reinforcement for a minute and look at two rising demands, sustainability and, well, speed. Let's start with sustainability and RPTG.
Yeah, the emphasis on sustainability is changing the industry, and fast. RPTG is just a filament made from recycled PETG.
And where does that recycled material come from?
It's usually sourced from industrial waste, from the virgin filament production process, or from rigorously sorted and cleaned failed prints and scraps. It's a great way to close the loop.
Our sources actually mention some specific companies doing this, especially over in the Czech Republic plastic guys, EcoM, Filament PM. It's pretty cool that this is becoming industrialized.
It is.
So what does the user actually give up for that lower price and, the ecological benefit?
The good news is that modern recycling is excellent at keeping the easy printability and low shrinkage. The key trade-off, though, it comes down to the science of thermal degradation.
Meaning what exactly?
Well, when you melt PETG down multiple times, the long polymer chains can suffer scission. They basically break into shorter fragments.
And shorter chains equal what in practical terms?
They mean a slight but measurable reduction in the ultimate strength and toughness compared to a truly virgin material. Now, for many common applications, you'd never notice the difference. But it is there.
And I imagine color consistency could be an issue.
That's the other obvious one. Since you're recycling various inputs, getting an identical color from batch to batch is a huge manufacturing challenge.
That makes sense. Okay, let's pivot sharply to speed because this is redefining 3D printing right now. We have to talk about hyper-PEG. With printers now hitting 300, 400, even 500 millimeters a second, the filament has to keep up.
Absolutely. The limitation now is rarely the printer's movement. It's the flow rate of the plastic. High-speed or hyper-PETG has a modified chemical composition. It's designed specifically to dramatically increase its melt flow index, or MFI.
Okay, MFI, that's another one of those critical technical terms. Let's ground that concept for everyone.
Think of MFI as the material's viscosity when it's melted. Standard PETG is like molasses. It's thick. It's slow to move.
Right.
High MFI hyper-PETG is more like a thin syrup. It melts faster, and it achieves a much lower viscosity when it's molten. And this is essential because printing at 300 millimeters a second is pushing a phenomenal amount of material through the hot end very, very quickly.
And if you try to force molasses through a thin straw too fast, the pressure just builds up and the plastic can't melt in time.
Exactly right. That high back pressure can lead to grinding the filament, under extrusion, all sorts of cold extrusion defects. By increasing the MFI, the polymer flows faster and more uniformly, which allows for those incredible speeds without sacrificing quality or, crucially, layer adhesion strength.
Yeah.
This material is purely optimized for volumetric flow.
Okay, so let's move to our final specialized variant, and this is where it gets really interesting. Critical safety applications. Flame retardant PETG, the V0 standard.
This stuff is paramount for electronics, for industrial equipment, Really, any area where the risk of a fire propagating has to be minimized. This is self-extinguishing PTG that meets the really rigorous UL94 V0 flammability standard.
What does V0 specifically guarantee a user? How is it different from, say, a V1 or V2 rating?
The V0 rating is the gold standard for thin materials.
Yeah.
It means that when the material is set on fire, the flame has to put itself out completely within 10 seconds. And, crucially, it also mandates that absolutely no burning drips can fall from the part.
Oh, that's a big deal. A burning drip could ignite something else below it.
And V0 eliminates that risk. That's why it's so essential for housing critical circuits.
It makes perfect sense for enclosures, server parts, components, and engine bays. But to get a plastic to do that, to be self-extinguishing, must require some massive changes to the chemistry. What are the trade-offs?
You are right to question them. The flame retardant additives, they're often mineral or phosphorus-based compounds. They do tend to slightly degrade the overall mechanical performance. So you get slightly worse strength and impact resistance than standard PTG.
But that's not the biggest problem, is it?
No. The most important operational drawback is significantly higher hygroscopicity.
Significantly higher. Can you quantify that? Why is it such a nightmare to keep dry compared to regular PTG?
The additives themselves, the things that make it V0 rated, are much more prone to absorbing moisture from the air than the base polymer is. So if you leave V0 PTG out overnight, it can become severely contaminated way faster than almost any other filament.
And if you print it wet?
You will see a spectacular failure. Steam bubbles popping at the nozzle, you get pitting on the surface, and layer adhesion just fails, making the part functionally worthless. Thorough drying, we're talking 65 to 70 degrees Celsius for 4 to 8 hours. It isn't optional. It's a prerequisite for any successful V0 print.
So in choosing that ultimate safety, you are massively increasing the operational difficulty.
You are. And this raises an important point. When you're dealing with a life-critical standard like V0, the manufacturer has to guarantee that consistency batch after batch. The engineering challenge shifts from strength or speed to purity and compliance.
So what does this all mean for you, the learner? We started with the generalist, with standard PTG, but we've quickly covered this whole spectrum of high-stakes specialization. We've defined the need for ultra-stiffness with CF, for impact toughness with GF.
Addressed economy and sustainability with RPTG, conquered speed with hyper-PTG.
And met the highest fire safety standards with V0.
And if we look at the bigger picture, this just confirms that modern FDM printing isn't a generic hobby anymore. It's matured into an engineering discipline where your success is fundamentally tied to choosing the perfect, optimized chemistry for the job. You're not just printing plastic. You're deploying a material tailored for a specific requirement.
It's not just about the printer anymore, it's really about understanding the polymers. So here's a final thought. We've seen that recycling material into RPG can slightly reduce mechanical properties and it can introduce variability. Yet at the same time, we have materials like V0 PTG, where consistency and precise chemical content are absolutely paramount for meeting life-critical safety standards. How do manufacturers navigate those conflicting pressures of maximizing recycled content while also maintaining the uncompromising certified consistency required for something like a V0 flammability rating? That is something powerful for you to mull over as you plan your next high-demand project.